humans is not enough. You also got to bioengineer what you're going to.
Well, that's why I said the planets, yeah.
But the time scale's so slow, the changes that you have to make are going to
Yeah,
be
I'm
minuscule.
going to talk about that too. Basically, what happens is you move a small number of colonists and astronauts onto another planet, and you leave the main population of Earth there to die. And that policy is not so cruel as you might think, because what's happening?
I'm not sure.
Oh, okay. Everybody's making signs.
Very good.
Yeah.
I had a theory where we could all like just come down in ships. We would be living around the Earth in the sky. We would take ships to come back down to Earth to take care of the animals and the plants. But we're really not meant to live on the Earth, but just slightly above the Earth, and we would just come down and.
Yeah, such things have been said in sci-fi stories.
Okay.
I personally don't think that's a practical solution, but it's an interesting, it's a charming idea. Okay.
So, what sets off a sulfuric acid cycle, like on Venus?
I don't think that's a concern of ours because we have to be off the Earth before that happens.
Okay.
But you're saying
Water and SO2.
what starts it? I don't know.
Well,
I don't know.
yeah,
Water and SO2, sulfur dioxide.
right. But so sulfur is fairly plentiful on Earth. I mean, I thought Earth and Venus had similar.
Hey, we're on page 3. We're doing great. Next question. Could we move the Earth farther from the sun? Somebody has calculated that we could steer massive near-Earth asteroids into gravitational slingshot trajectories past Earth. The NEAs would lose angular momentum, possibly falling into the sun, and Earth would gain angular momentum, shifting into progressively larger orbits. Dropping NEAs into the sun would certainly seem to alleviate the impact problem. Eventually there'd be none left. Unfortunately, having none left is a big problem because the total mass of all the NEAs is so tiny and their angular momentum is so tiny that it moves, you know, if you captured all of that angular momentum, it would move the orbit of the Earth out like 0.1% or something like that. So that ain't gonna fly. However, we might be able to recycle the NEAs. You bring them past the Earth, you make sure that the trajectory after the slingshot event on Earth takes it up to Jupiter. You then do a couple of slingshot passes around Jupiter, bring it back down to the Earth. You could have just one NEA, and it's more effective than all the thousands and thousands that we would have now, assuming you're going to throw them away after one pass.
How do you get up to Jupiter?
Yes. Well, there's several conservation laws that you have to satisfy. One is conservation of angular momentum, the other one is conservation of energy, and so on. Normally you worry about heat energy. In this case, heat energy is irrelevant because celestial mechanics is dissipation-free. It doesn't produce heat. It's interesting. Suffice it to say that probably you have to do more than one pass around Jupiter or another planet. Probably you need to involve 3 planets, actually, to conserve all the required conservation laws. Either Venus, Earth, Jupiter, Earth, Jupiter, Saturn, something like that.
How far can you move it before you start perturbing the orbits of all the other planets?
Yeah, yeah. In particular, what happens when the Earth falls into a 3-to-2 resonance with Mars? That probably means that in addition to moving the Earth outwards, you're going to have to move Mars outward too. That's not as bad as you might think because Mars only weighs 10% what the Earth does. So you worked you have to work 10% harder because now you're pushing Mars outwards as well as Earth.
Would it be easier to put an object or a group of objects, say in the Lagrangian point between Earth and the Sun, and just create a permanent partial eclipse?
That's
That
about
act as
page
sunscreen?
5.
Okay.
There's 2 ways of doing it, and neither one is perfect. Okay. Yep. Oh, in fact, we're on page 4 now. That's cool. We're using Jupiter as a source of angular momentum. Jupiter's angular momentum in Earth units is 725. Jupiter's kinetic energy is 61. Interesting numbers. Suffice it to say that, you know, we have to mess with both kinetic energy and angular momentum. Paradoxically, we are increasing Jupiter's kinetic energy, we're decreasing the Earth's kinetic energy when we do this. Why is that? Jupiter is going closer to the Sun, losing angular momentum, moving faster. It has more kinetic energy. The Earth is moving away from the Sun into higher orbit, less kinetic energy. This is one of these things I was talking to you about. Non-intuitive things in celestial mechanics.
Total mass effect.
Let's also look what happens when, let's suppose we're moving Earth and Mars outwards, and we run into a triple thing with Jupiter and Mars and Earth. A triple resonance of 2 to 3 to 6. Every time Jupiter goes around once, Mars goes around twice, Earth goes around 3 times. That's a stone wall that's going to be hard to climb over. And if you succeeded, I think one or both planets, Mars and or Earth, would become uncontrollable, end up in a very eccentric, very inclined orbit, which would be the end. Because talk about climate shift. If the Earth is in a comet-type orbit, forget it.
What would happen to the asteroids under those conditions? You got the planets, we're talking about planets. Now you have all millions of asteroids.
Oh, yeah. Oh, yeah.
What happens to those guys?
Yeah.
Are they moving away?
Well, the
crashing into
asteroids that found themselves in exciting orbits because of Jupiter effects, those all crashed into each other and
have we
splitted
shoot Galilee
themselves.
and the inner planets? Because of
And you know, that's where our fireballs come from, is shattered asteroids, right? So imagine you introduce 2 more massive planets, Earth and Mars, into that region. Then you're going to get a bunch more asteroid collisions, and maybe a bad idea.
Yeah, I mean, we'd expose the Earth to more asteroid collisions, probably.
Yeah.
Well, but you're talking about a time in the future where if we're moving the Earth, we've clearly mastered moving asteroids.
Yes, well, that's how we're moving it.
Exactly.
Yeah,
We're
right.
grabbing asteroids and bringing them to
Right.
slingshot orbits.
Not a problem.
Yeah.
Well, yeah, except that
Yeah, well,
But now we have a lot more asteroids to deal with.
we need to keep track.
Over millions of them.
We need to keep track of like 1 million asteroids. And you say, yeah, we got computers. Well, if you miss
Right.
1 asteroid,
You don't have computers anymore.
A million years from now, computers will be able to.
that's how the dinosaurs lost all their computers.
I'm starting to think we should just go
Okay,
off the 5th dimensional beings.
let's put a shield at L1. Right? L1 is the first Lagrangian point. It's the place where an object about 1 million miles closer to the Sun than the Earth can be in a stable orbit, semi-stable orbit. Basically, I hate to pick up this because I said I wasn't gonna, but if you look towards the sun, and if there were an object in the L1 region, and you watch it for a while, maybe you'd see it doing something like this. Like going around in a little circle or an ellipse of some sort. That's called a halo orbit. And spacecraft have been put into halo orbits. I think that's in the Earth-Moon system, is that correct? I see you nodding your head.
No, I just knew you were, that they put in halo orbits.
Yeah, yeah. I'm not sure whether that's Earth-Moon L1, which I call Moon L1, or whether it's Earth L1, meaning Earth-Sun.
I think it's Earth-Sun.
Earth-Sun?
Well,
Okay. Okay.
Someone
Anyway,
put both.
if you put a bunch of sunscreens out there, then when you're looking at the sun, here's the sun, and somewhat below the center of the sun, you see this, what looks like a humongous sunspot. And during the course of a day, it shifts to the left and right. And if you go to a different location on Earth, it shifts up or down. If you're at the subsolar point, then the sunscreen is right there at the center of the sun. And something that big is going to block off somewhere on the order of 1 or 2% of the sun's light.
Yeah, but something that big also catches a lot of solar wind.
That's right.
How do you keep
That's
it,
how
how do you keep it there?
That's how it keeps itself there. Each one of those little, each one of these things are thousands of little subscreens. And each subscreen has solar sails. And they have to be able to maneuver, otherwise they crash into each other all the time.
So you tap into the solar wind?
Yeah.
I think we should just abandon all of that. With the technology that's going to happen over the next several million years, even a billion years, I think we can build very, very nicely a Dyson sphere and take everything with us.
Dyson spheres are
I
hard.
like that too.
Of course they are.
Dyson spheres are way harder than anything we're going to discuss.
What I'm saying
including
is-
the 100 billion year
You're
solution.
still talking about a billion years of technology, so I'm not so sure it's
I
a
know,
real
imagine
problem.
Where does the material for a Dyson sphere come from?
That's what technology's all about.
You can't make something out of
I
nothing.
don't know.
You
Hey,
have
look,
to disassemble.
Do you know that?
In a
Jupiter
billion
and
years.
Yes,
cells.
assemble Jupiter.
In a billion years, we will have abolished the conservation of mass, right? So we can just bring our materials out of nothing, right?
Don't think inside the
Congress
box.
could do that next year.
Think inside the sphere.
Might be able to
Yeah.
process the stuff that's in the sun.
Pi will equal 3.
So now, we've got a thing that blocks the 1% of the sun. Whenever the sun gets a little brighter, well, you keep adding more of these sub-screens. And you keep adding more of them and more of them and more of them. This thing was originally, let's say it's 1% of the shielding, then its radius is 1/10 of the solar radius, because that's 1% of the Earth. And how big is it actually out there? Well, it's 40% the size of the moon. So it ain't solid. And in fact, it's made out of a whole bunch of individual things that are not connected to each other, except maybe by
Mylar
lightweight
sheets.
cables.
Mylar sheets. Doesn't have to be thick
There's
either.
arguments in favor of having them connected to each other by means of cables and winches. There's arguments in favor of having them completely separate and just avoid each other the way cars on the freeway avoid each other, which is not very well. Yeah.
So if they were actually connected, would you have them rotate to keep
You
them
indeed
stable?
would. You indeed would. And in fact, there is a scheme which you can talk about at the restaurant.
I'm not going to the restaurant.
Okay. Well, if we have time. Remember that thought. So that's one type. At some point, the sun is going to get so big and so bright, so big and so bright, but contrary to that idea, it's also the surface brightness of the sun is decreasing because it's becoming a red giant. And so eventually, the design that you want, let's say this is a red giant sun now, you want a screen that's this big, and then in order that the Earth is in complete darkness, you have a little pinhole in the center. And light is coming through that pinhole and illuminating the Earth. The problem is, when that pinhole gets to be the size of Uranus, and this screen is bigger than Jupiter, and we're supposed to run out of materials here. And so you want to go to a different design. And so instead of having this at L1, you have it in low Earth orbit. And it turns out, I think, my back of the envelope calculations say, for a small amount of sun absorption, like a few percent, you want to be at L1. For large amounts, like the sun is 10 or 20 times brighter than you want, then you want to be in low Earth orbit where your screens are. And so here is something. Here's the Earth. This is a view of the Earth as seen from the sun. Do you have a question? I guess not. No. Okay. There's the Earth as seen from the sun. Now in low Earth orbit, in approximately polar orbit, and in fact in sun-synchronous orbit, we have a whole bunch of subscreens, and they look sort of like this. And there may be 1,000, they orbit maybe 1,000 miles up. And since these orbits all intersect, they better all be at different altitudes, or else you're going to have the mother of all freeway collisions. And this angle is like, that line is perpendicular to the Earth's orbit, and that angle is like 10 degrees or something like that. There's a sun-synchronous orbit. All these orbits precess around, due to gravitational effects, they precess around in a period of 365 days. Artificial satellites are routinely put into these orbits. They are slightly retrograde, so this velocity vectors here, the motion is all this way, and the Earth is, orbiting. The Earth is rotating this way. So these are retrograde orbits.
And you're saying this is easier than a Dyson sphere?
Way easier than
Yeah,
the
it's
Dyson
much smaller
sphere.
than a Dyson
This
sphere.
is teeny tiny. This is the size of the Earth.
The Dyson sphere has to be
is the
significantly
size of the
larger
sun.
than the sun.
Millions of times bigger than the sun.
What is a Dyson sphere?
It's a thin shell that you put around a star, and then
You live
with
there.
it.
You live on the inside of a sphere that encapsulates the sun, and that way you can harness all the energy, all the solar energy that's being put out by the sun. And
You're walking on this. You're walking on the inside surface of it.
enormous amount of
Yeah,
space,
but
which
the-
spread and grow and.
The reason it doesn't seem to impress me very much, it's like saying that you ought to have 4 nuclear bombs under the hood of your car because that has more energy than the engine that's in there now.
But you've already proposed a sunshade the size of Jupiter as a means of getting to. Or-
No, you
Well,
don't
no, that's
want
if
to
you
go
put it at the
there.
L1
Yeah.
point.
Well, as soon as that becomes cheaper, then you go to that. And you can see that at any point on Earth, like Michigan, there's a sunrise on Michigan. The sun is humongous. You can almost look at it without burning your eyes because the surface brightness is so low that it's that big, instead of that little speck in the sky. And then you go into the shadow, and then at sunset, you get another dose of sun at that point. And these 2 sections are calculated to keep the Earth at the temperature that you want it to be.
And how long would this process take? I mean, how long would this process last?
Well, you have to keep adjusting it, as with
Quote, unquote.
all the other sunscreen designs. So eventually, the bottom line is going to be that no matter what materials you use, both of these want to be super reflective materials. No matter what material you use, eventually it's going to melt, even though it's the best mirror that we know how to make. So it buys you some time. And it might be hundreds of millions of years it's probably still worth doing. Might be a billion years. Still worth doing. One argument for having these all separate and maneuverable is what happens when you have the closest asteroid approach in a million years, and it's going to come right through there. And it's going to pass within 200 miles of the exosphere of the Earth. You got to move those sun shields out of the way to let it through. So they got to be individually maneuverable. Yeah.
So at our current rate of production of space junk in orbit around the Earth, I think we'll be there in 2 billion years.
We might be.
Okay.
Might already
Help
be
itself itself.
Might already be there.
But what happens?
But
what
it's not
happens then is-
controllable.
Good job, Chuck. That
What
was
happens
good.
then is that they collide, and there's this runaway collision phenomenon.
So you have more of them and they're smaller after
You end up with a
collision, right?
disk.
Get them geosyncers.
You end
Yes,
up with
that's
a,
true,
with a
right.
Saturn-like
Yeah.
disk around the Earth,
Yeah.
around the equator. And that's really good for shading the equatorial regions, but Michigan is stuck out of the
Okay,
shade.
the reason I'm actually not finding it this crazy is because in the same time, assuming not all of our resources are going to building the shields, by that point we ought to have AI that can control all that stuff without whatever humans are
Yeah.
out about even, being concerned about.
That would probably be
But we
what's
need a
building
space
that.
centrifuge to get the materials up to maintain
Each one of
this.
those is very interested in a little section of space-time, which is where it lives. And so when it's looking up in the universal ephemeris of every piece of space junk and every asteroid, says, holy cow, I'm due to be hit next year. I'm going to move out of the way. And nobody has to tell it to do so. It has a built-in instinct to
I'm
get
going
out
home
of the way.
tonight and I'm
AI.
giving money to a bunch of transhumanists to build an AI to control your sunscreen.
Well, the cyborgs are the
Ah.
replaced humans. Probably
Right,
won't
yeah.
have
They'll be
ideas.
building it anyway, we
Robots
won't be
going.
building it.
We're on page 6. This is really amazing.
But you're on
Can we
time.
move Earth's culture to other cooler planets as the sun brightens? The answer is yes. And note that I refer to Earth culture, not Earth's population, because moving the population is much harder. What we do is move a small number of carefully selected astronauts and pioneers. A small number might be 100,000. On the new planet, they gradually build up their population. What happens to the majority back on the old planet? We leave them there to die.
Oh.
This policy is less cruel than it seems. Their population will dwindle very gradually by human standards and historical standards. But their population will dwindle very quickly by cosmic standards. And here's a little calculation. Let's establish a policy of reducing Earth's population by 10 parts per million every generation. And we'll ask the question, and this 10 parts per million, so that you get a feel for what that means, is that more or less each family will consist of one father, one mother, one child, and 1.99998 children.
We need to decrease that number.
Now, I claim that that number is,
I know kids that are
in human
0.99.
terms, that number 1.99998 is indistinguishable from 2.
Right.
So this is what I mean by minus 10 parts per million per generation.
But Dave, on the time scale you're talking about, why would you even assume you need binary parents?
Good question. That is a good question. Yeah, good question.
I'm looking at.
And evolution, we're talking about times that are long compared to the time to evolve a new species.
Right.
Yeah.
I mean,
However,
basically,
show me
per
an example.
parent, you need 0.99999 children.
You added another 9?
No, I changed that 8 to a 9
Oh,
and
okay.
removed,
Yeah.
subtracted 1.
Oh, well, yeah,
I
because.
divided by 2 is
we've-
what I
We've
did.
eliminated that one, so then this one.
Well, I wouldn't say that. Excuse me, I'm kind of attached to
I
that
was
one.
about to say. I was about to challenge Diane and say, give me an example, and then I realized there are parthenogenetic vertebrates.
Well, no, but zero, it would be 0. The replacement rate would be, or the a little bit less than replacement rate would be 0.9.
I'm just saying that if we're dealing with
Yeah.
bioengineered humanity,
Oh, yeah.
hundreds of
You're
million years in the
rid of the Y
future,
chromosome.
binary parents are not a requirement.
Not a requirement, yeah.
Right, read or listened to a recent science fiction book. There is a place in the solar system we could go that we wouldn't care if the sun became a red giant or
Yes.
white dwarf. Kuiper belt objects. The people in this hollowed out Kuiper belt objects, and some of them are
Oh, yeah.
hundreds or up to almost 1,000 miles across.
Hollowed out, yeah, sure.
They had artificial gravity also,
Sure,
but
yeah. Well, we'll get to that in a minute. All right. So, given that reduction of population rate, how many generations will it take to reduce Earth's population from, say, 10 billion down to 1/10 of a million? The answer is 1.15 million generations, and at 30 years per generation, that's 35 million years. That's a very short time by cosmic standards. So if we could get the people to adopt that number in 35 million years, the Earth is almost uninhabited, and nobody has died. Yeah, except by,
I think you're-
Well-
death.
you're taking into account people still dying at age 80. What if they lived for
Oh, yeah.
1,000 years
Yeah,
or more?
that's true, that's true.
It's a very, very big.
1,000 years is a very short time relative to 35 million years. So it doesn't matter that much.
Gary
Doesn't
Ross
matter
is
that much.
1,000 years.
It's only like 300.
He'll be one of the ones selected to go to the other planet.
Yeah.
Yeah, well, that's a very interesting story. You could write all kinds of sci-fi stories set in that kind of situation where everybody wants to have one of their descendants, one of those astronauts and pioneers. And then it would talk a lot about how this is enforced. Basically, you enforce it by, instead of killing off your criminals, you just castrate all their children, and people, oh, you can't do that. Well, it's one way of enforcing that number.
Okay, but instead of going with these sort of medieval bioengineering solutions, again, we're dealing with technology tens of millions of years in the future. What if we have virtual humanity?
If we've been downloaded into some
You
core.
still gotta protect the server. I understand the virtual part, but what justification do you have for using the word humanity?
Just need a really big.
Transhumanist species.
Yeah.
We're going total science fiction here.
So,
Thank goodness Gary
once
Ross
you've,
isn't here.
once you've got your population of Earth, once you get the population of the Earth down to 1/10 of a million, then all those people become refugees. And you deport all of them to the new planet. You've now, how many people have you had to move? You moved 100,000 astronauts and pioneers. Now you're moving another 100,000 refugees. That's really easy compared to moving 10 billion.
What was the time frame
You're
between the first group leaving and
30
this second group coming?
30 million years.
Yeah, over 30 million years, these people no longer want anything to do with them.
They
They're
are
like, we're
separate.
not taking them.
They're
We're not taking
They're
them.
separate species.
Exactly. We're never picking them up.
No Terran scum welcome.
Well, actually, the first bunch of people would be assigned the job of terraforming 2 planets, Ceres and Vesta. So the new group go to Vesta, and now you've got both asteroids colonized. with
No.
two different species.
Well,
There's all
over
kinds
making
of-
some
you could
bogus
still keep
assumptions that
in, you could
humans
still
can
keep
even
in touch to
survive
serious
in that low
investment.
gravity.
Oh, sure. We're on page 7.
I mean,
All right.
one of the things you're talking about is moving cultures. One of the things that in the stories I was listening to recently is whole planets populated by individual Earth cultures. So
Sounds terrible.
some of them you wanted to avoid.
I don't think I think that would be difficult.
ISIS, for example.
I think that would not be an equilibrium situation.
Yeah.
I think you're going to have, well, suppose all the countries in the world suddenly vanished and all we had was the U.S. I think very soon we'd have some wars going on within the U.S.
I don't think you even have to do the first part of it.
Yeah.
Right, it's the same thing. You have a solar system populated by a bunch of different groups that are going to fight just like countries fight.
So it's a lot of creative thinking at the current knowledge of what today's information is, but information changes constantly. So the past 100 years, scientists, astronomers will be thinking differently than what maybe in a billion years to come.
That's a very hopeful standard, and it's probably closer to the truth. Because one of the things that humanity is pretty resilient.
Yeah.
And I think that all the nonsense that you're seeing going on in the world today is probably going to improve.
Let's
Teach
make
the
a...
future generations and present generations is tolerance of one another.
Yeah.
Each person is a culture in and of themselves, whether they
Exactly.
want to believe it or not. Each one has their own unique characteristic and personality, which cannot be compared to someone else. Each person is like a diamond in the rough edge, so no matter how you cut the stone.
Well, but for me, the problem's always been that we came from a primate that fights with fellow primates over resources. That's just a part of our heritage. How do you'd have to engineer around it.
Well, the miracle is...
When we evolve, you know, like the body has changed, you know, from what we might have been, you know, and then how we are maybe going to evolve in the species and how we will look different already. Just that idea of that alone, you know, in science terms, you know, and how we will do things then what we do now.
And I also believe too that if we all just came to God, we wouldn't be fighting as much. And I think that if we were raised, you know, our parents raised us properly, and we all became this God-centered universe, I think all of the problems, 99.9% of the problems would be, we would be almost in utopia right now.
Before we go too far, I'd like to hear the end of Dave's speech. I think it's on his last page. Let's do that, and then we can discuss if we have
I
time.
think this will never get to that point because we're gonna blow each other up with nuclear weapons. There's enough heat.
That's page 8.
Well, we're at the top of page 7. I'm just going to make a list of the planets that we can inhabit. And my list says the Earth, the polar regions of the Earth, the polar regions of the Moon, underground. The Moon, you can control the temperature of the poles much better than you can control the temperature of the Earth. Much better. The Moon doesn't have weather. You can ignore all those weather problems that you have on Earth. Next is the polar regions of Mars, underground. No, Mars. Anywhere on Mars.
Underground.
Underground, yeah. And I explained why a little while ago. Asteroids in the inner part of the main belt. Asteroids in the center part of the main belt. Asteroids in the outer part of the main belt. You choose your asteroids carefully because you want them to be in circular orbits.
Like
A little bit of
series Vesta.
eccentricity can really spoil your day.
Even on the inside?
Then, yeah. Ganymede and Callisto, underground.
Alright.
Titan, I'm assuming that you can terraform Ganymede and Callisto when you have water and air and all the usual stuff.
Isn't that Jupiter radiation environment pretty awful?
Io, yes.
Callisto's pretty
Europa
far out.
They're all pretty zapped.
But we're going underground.
We're already dealing with long-term space travel. Let's assume we solve the radiation.
We
Yeah,
probably
sure.
will, that's the point.
Next is Titan, underground, of course. Titania and Oberon, underground. Triton, underground. Note on Triton. Triton is moving in retrograde and will, quote, soon be destroyed. Whether it'll actually crash into Neptune, probably not, but it will be dismembered and turned into a ring, which will continue. That'll be a big accretion disk, and it'll be very pretty, and it'll probably roll into Saturn. So we
could
need to
save
rescue
Triton.
Triton by raising its orbit.
Yeah.
Because we're going to need Triton when, Titania and Oberon start to get too warm.
Yep.
And let's see, Neptune is at 30 astronomical units out there, so the sun could get to be 900 times brighter than what it is now. So, yeah, it might be a nice, cool place to go. And the sooner we raise Triton's orbit, the easier it will be, because it's going deeper and deeper into the, retrograde. It's going deeper and deeper into the gravitational well, and it gets harder and harder to get it back out the longer we wait.
Even Neptune's gravity is close to our gravity. Is it Neptune or Uranus's gravity?
Yeah, but we can't live on either one because the solid surface is too far down.
Okay.
What if the sun gets so bright that Triton is uninhabitable? Here's where I get to the 100 billion years thing. In 2 or 3 billion years, there's a good chance that a dwarf star system will pass within 1,000 astronomical units or so of our own system. If we see that that's about to happen, then we research it and we discover that there's habitable planets that can be terraformed, and we just jump across. Now we have to deal with the whole velocity difference problem. but that problem is present if you're going to
Anywhere.
going to Betelgeuse or wherever.
Everything in space
You've got a
is
humongous
going
velocity difference problem. And if the thing is only 900 astronomical units away at closest approach, then you just hop across. You don't even need a lot of supplies. You don't need millions of years of supplies on your spaceship. So just jump across. And the chance is excellent, in fact, way greater than 50%, that the lifespan of that star, instead of being 10 billion years, will be more like 50 billion years, 100 billion years.
That's right.
So forget this, 3 billion years time scale we've got here. If you hop across to the right star, you've got 50 or 200 billion years ahead of you.
But it's gotta be a red dwarf.
Red dwarf.
Yeah, the red
Dave,
dwarf
I
also might be
suggest,
highly
practically every star is
electromagnetic.
a red dwarf.
There's
With
a lot
a
of
possible
disturbance
exception.
on that, but you might be able to control that if you're the
Maybe there's a lot
technology.
of brown dwarfs. Maybe there are more brown dwarfs than red dwarfs. I think the jury's out still on that
Yeah,
one.
But brown dwarfs aren't really helpful.
no, not terribly. They're 2,000 degrees
Well,
Yeah,
surface.
that'd be pretty damn close.
Well, that's pretty close, if you're close enough to them. But again.
Hold that thought.
on the red dwarf, because the light from the red dwarf might be too red for chlorophyll to work well, whereas for a few minutes every day, there's a flare and the plant does a lot of photosynthesis real fast. I suspect that plants are smarter than that and could evolve chlorophyll that would deal quite nicely with low energy photons. But it's an amusing thought. Yeah.
One thing you haven't talked about, because, well, the thing we do know is that the tilt of the Earth determines, whether we're in summer or whatever. Well, how about if you sped up the orbit of the Earth? Instead of a 24-hour day, had a faster time. It would spend less time baking, have more cooling periods. It's like, how much time does the egg sit in the frying pan?
Yeah.
Or
Interesting
if you
thought.
change the tilt of the Earth a little bit.
I think you have a better chance of changing the tilt than you have of speeding up the Earth.
Yeah.
And yeah, we could speed up the Earth, just bring Mars in and crash it into us. But that would definitely speed up the Earth. But whether we want to do it is another question.
Option B?
Actually, over this long period of time, what would the moon be doing to the Earth's rotation rate? Over that period of time? The moon presumably by the time the moon escaped or, well,
The moon is moving away.
Yeah, the Earth is slowing down, and the Earth will continue to slow down even if we could wave a magic wand and make it bigger. Because without the moon, we've still got solar tides, and the solar tides are still slowing the Earth.
Well, but if we're moving the Earth with asteroids, we can place the moon where we want to.
Yeah,
that might be tough.
maybe.
You know, the moon is, compared to the asteroids, the moon is a mighty big object.
Yes.
Hey Dave, eventually the moon's gonna get to the Lagrangian point, right? At that point, can we do something with the moon to draw for a sun shield? Would the moon be an option or a possibility as a sun shield?
Well, the moon is unmanageably heavy.
Yeah, but
it's already spiraling
But
out.
the interesting thing is that that's already happened. That's where Mercury came
well,
from.
yeah.
Mercury, in my opinion, Mercury escaped from Venus through the L1 point.
That's an interesting
But
premise.
the moon
That's something I
might-
can talk.
The moon might be a convenient source of materials for the sunscreen.
Oh yeah,
Right.
that
That's a
sunscreen,
good point.
this sunscreen did not come from the Earth. That sunscreen probably came from near-Earth asteroids, and maybe from the moon. But even this one also came from not from the Earth. In terms of energy, inconvenience, and all that stuff, the surface of the Earth up to low Earth orbit is farther away than any other place in the solar system down to near Earth orbit. You burn more fuel getting from here up to low Earth orbit than you burn getting from Uranus to low Earth orbit. But you get there faster.
Well, from low Uranus orbit to low Earth orbit, I imagine.
Because you gotta be,
Well,
you
maybe
gotta be,
from one of the moons of Uranus.
Yes.
right, not from Uranus itself.
Well, yeah, it's hard to get up through the atmosphere of Uranus. So that's what I got for you today.
I have a question.
Yeah. What stock should we invest
Behind
in?
you. Sorry.
I guess we could take a couple or so more questions or comments.
Oh, well, in response to this gentleman, I think it's a kind of a miracle that individual people resemble each other more than they differ from each other. That's what makes our society possible.
Yeah.
If we resembled each other as much as we resemble, say, a frog, then, and each person was that different, then where's our civilization? Where's our society? It's impossible.
Probably get along better.
On Tatooine.
Well, that's the problem. You have a system living on Ceres with that low gravity, if you can even survive human, you're gonna become long and gangly and thin and.
Well, Dave mentioned to me before he got started tonight that he is going to the restaurant. So this discussion can continue there for those who are so inclined. Where is the restaurant?
Restaurant is, we are no longer going to the Applebee's. We are now back to the National Coney Island, but not the old National Coney Island. We are on the at the National Coney Island on Van Dyke, just north of 12 Mile.
On the right side.
On the east side, yes.
East side. Right side.
Yeah.
Okay. We do.
Assuming all this can be done, such as developing the space culture, such as space.
Thanks for coming, everyone.
Yep.
Thank you.